Hello everyone, welcome to the lecture 59 on the course Diffusion in Solids. So today, usually the last lecture of the week is the tutorial lecture, but today the second last is the tutorial because this is the last week, and the last lecture I intend to have a revision of some important concepts that we had done during this course. So that will be the last lecture. So that is a small change from the list that was given in the introductory video, this last bit. So we'll take the tutorial in this lecture and the revision in the next one. So the first question is which of the following statements are true about a glassy structure? So the first is it contains a high fractions of dislocations and grain boundaries. This is not correct. In fact, glassy structure does not have dislocations and grain boundaries because grain boundaries, for example, are nothing but misorientation between the grains. So there are no grains in structures, so there is no dislocations or grain boundaries. Second is it displays sharp peaks in the X-ray diffraction pattern. This is also not correct. In fact, you have amorphous hump that is characterized. So you can see here this is for the glassy structure. Here it is for the crystalline structure. The third option is the structure is metastable and undergoes relaxation on heating. This is true. So the glassy structure, as we know that it forms on the fast cooling. So the equilibrium structure is not the glassy structure, and it undergoes relaxation when we heat the glass. A long range order is absent. This is true. So a long range order does not exist in glasses. Its structure is characteristic of the melt from which it is cooled. So therefore the correct options are C and D. Question number 2, the enthalpy of a glass at any given temperature is a function of its thermal history, true or false. So this statement is again true if you look at this diagram that we had seen where the y-axis is enthalpy or the volume. If you take any temperature like this, the enthalpy depends upon what is the rate of cooling. So if the glass is cooled very fast, then the enthalpy will be more. If the glass is cooled slowly, then the enthalpy will be less, and so on. So therefore, the enthalpy of the glassy structure is dependent on the cooling rate. So this is true. Now, so refer to the figure below and identify the glass transition temperature. So this is a DSC curve shown here, and we need to see which of them correspond to the glass transition temperature. So here this we know that this T4 represents the crystallization temperature. So the correct representation of the glass transition temperature is this. Remember, it's not a first order transition, so you don't get a peak but it is a simple, it is a increase and is a change in the inflection. So this is the glass transition temperature. So the correct answer is A1. Question number 4. The rate of crystallization from a melt is maximum at an intermediate undercooling. Explain. So the intention is to say that the rate of crystallization is not maximum at the melting point or near the melting point. It is maximum somewhere in between. Why is it so? Or it is not higher as you go down the temperature. Why? There is a intermediate temperature at which the nose exists. So here the reason is as follows. Basically the crystallization proceeds by nucleation and growth. So now for the nucleation to occur, the driving force is given by this temperature. So let me tell again. So the rate of crystallization depends upon two things. One is the driving force, another is the diffusion. So the diffusion means if the diffusion is fast, then the nuclei can form fast and grow fast. So the driving force is inversely proportional to the temperature at which you are. So that means the farther you go away from the melting point, higher will be the driving force to transform into a crystal. So that is to say, this difference, the delta T, the larger this delta T is, then higher is the driving force. So if you go down and down the temperature, you will see that the driving force becomes higher, and that is favorable for crystallization. However, as you go higher and higher, lower and lower in temperature, then what happens is the diffusion, we have already seen that the diffusion decreases exponentially with decreasing temperature. So if you go further down the temperature, then the diffusion becomes slow. So therefore, these two, there is a trade-off between the two, and hence there is an intermediate temperature at which the nose exists, or a maximum exists. Moving ahead, identify the correct statement or statements about the structural relaxation of a glass structure. So the option number 1 is a more stable amorphous structure is obtained. This is true. When you heat the glass, a more stable structure is obtained. Second is density changes are large and impact the diffusion properties of glass. Density changes do impact the properties of glass, the diffusion properties, but those density changes are not very large. So B is not correct. Density changes are small and do not impact the diffusion properties of the glass. This is also wrong. As I said that density changes are small, it is all right, but they do impact the diffusion properties of glass. Then option D is extent of changes in physical properties is a function of thermal history and glass production route. This is correct. So depending on if you had cooled at a very fast rate, then during the relaxation the changes will be more. If you had initially cooled itself at a slower cooling rate, then you will see the changes during relaxations are less. So the correct options are A and D. Question number 6 is the initial decrease in diffusivity during structural relaxation at a constant temperature is attributed to. So if you see that we had seen this kind of a graph, that diffusivity decreases with time at a fixed temperature. So what is the reason for this initial decrease? Is it the creation of excess dislocations, creation of excess vacancies, annealing of excess volume and decrease in density, or annealing of excess volume and increase in density? So if you take the cue from the previous question, previous questions rather, we saw that dislocation and dislocations do not exist in the glass, and it is the excess volume which gets annealed out during the relaxation and leads to an increase in the density. So if the density increases, then the structure becomes lesser closed packed, and therefore the diffusion is slightly more difficult. So that's why the diffusion rates come down. So the answer is D here. Question number 7. Diffusivity during structural relaxation of a metallic glass at a temperature T is given by this expression. D of T is equal to 300 minus T by 3 minus T square by 30 into 10 to the power minus 15 meters square per hour. So here the T is in hour. That's why the diffusivity is also given in meters square per hour. Find the time averaged diffusivity after 48 hours of annealing. So we saw already this formula that the time averaged diffusivity can be calculated by 1 by T 0 to T d of T dash dt dash. This is a dummy variable, so we can use this expression here. So this is 1 by 48, 0 to 48, since the units are already given in meters square per hour, so we don't need to change this. So we already saw that integral of such expression. So this will be 300 T minus T square by 2, so it becomes T square by 6, minus this is T cube by 3, so it becomes T cube by 90, and you put the limits 0 to 48 divided by 48. So the answer will come out to be 2.67 into 10 per minus 13 meters square per hour. Moving ahead, question number 8. Which of the following statements are correct regarding the kink temperature observed in the Arrhenius plot of vitrolloy 4? So if you recollect this, we had seen that if you take the vitrolloy case, then you observe a small kink here in the diffusion Arrhenius plot. So it is exaggerated a little bit here. In reality, it is actually a change which is in fact lesser than this. So the kink temperature corresponds to the transition between the glassy and the crystalline state. This is actually false. The kink temperature corresponds to the transition between the glassy and the supercooled state. The activation enthalpies and pre-exponential factors in the glassy state are lower than those above the kink temperature. This is true. The kink temperature is higher for the higher elements, diffusing faster is amorphous state. This is also correct. This has been observed in the literature. And the kink is related to a change in the diffusion mechanism, but is independent of the thermal history of the material. This is false. Actually, it is reverse. So the kink is not related to change in diffusion mechanism, but actually it is dependent on the thermal history of the material. It comes because of the incomplete relaxation of the amorphous state. So the correct options are B and C. Coming to question number 9. So here refer to this image below. This is the image of ionic crystal in 2 dimension, and you see these letters A, B, C, D, E. They represent the defect, and here is the table, but this is not correctly matched. So your task is to match it correctly. So what is A here? So A, if you see, A is so cation is basically missing, and it has gone to the interstitial. So it's a Frankel defect. Then B, if you see that B is there is an impurity ion, there is a vacancy. So B is impurity ion plus a cation vacancy. C is a vacancy pair. There are 2 vacancies of different charges which exist together. So this is a vacancy pair. They form a pair because there is an electrostatic attraction. Then D is a missing of an anion and a missing of a cation together, which is a Schottky defect. And E is a impurity vacancy complex. They exist together. So this is how you have to match correctly. Next question, which of the following defects are dominant in silver halides? So here in the silver halides, what we had discussed is the cationic Frankel defect, which is the most dominant one. Now, in the question number 11, this you might have seen earlier this type of questions. So we have 2 statements marked as an assertion A and reasoning R. Mark your answer as per the codes here. So we have a statement which is an assertion that, for example, here in this case it is vacancy pairs do not contribute to ionic conduction. This is, of course, we are referring to the ionic solids, and reasoning is vacancy pairs are electrically neutral. So now if you think both A and R are true and R is the correct explanation of A, then you mark the option A correct. If you think both the statements are true but R is not the correct explanation of A, mark option B. So C is the assertion is true but the statement itself is false. The D is the assertion itself is false but the statement in R is correct. And if both the statements are false, then mark the option E. So this I gave because you may have such questions coming in your either assignments or in the final exam. So so that you can practice. So now coming to the question, we know that vacancy pairs do not contribute to ionic conduction. This is true because vacancy pairs are formed of oppositely charged vacancies. So if a cation is missing, then the vacancy has a negative charge. If an anion is missing, then the vacancy has a positive charge. When these two come together, they form a vacancy pair, and they are electrically neutral. Therefore, so both A and R are correct. And now we have to see whether R is the correct explanation of A. In this case, it is, because the reason vacancy pairs do not contribute to ionic conduction is because they are electrically neutral. So, in this case the correct option will be A. Question number 12 is also of the same format. Here the statements are as follows. The assertion is as follows, that in the intrinsic region the dominant diffusion mechanism of Ag is the interstitial C mechanism. So, first we have to check whether the statement is correct. So, this statement is correct. The dominant diffusion mechanism of Ag is the interstitial C mechanism. The reasoning statement R is Ag plus can make collinear and non-collinear interstitial jumps. This is also true. We saw that there is a knock-on process which is also involved, that is an indirect interstitial jumps. It can be non-collinear, it can be collinear if it is moving in the same direction. However, now we have to see whether this R is the correct explanation of A. So, this does not explain, the R statement does not explain why the dominant diffusion mechanism of Ag is the interstitial C mechanism. So, therefore, the correct option is B, that both A and R are true, but R is not the correct explanation of A. Actually, the dominant diffusion is interstitial C because the Ag plus interstitials are more mobile, and therefore, you see that they are the dominant mechanisms there. Yeah. So, moving to question number 13, addition of which of the following impurities to AgCl will result in a vacancy with -2 charge. So, if an impurity is added, we know that to maintain the charge neutrality, an equivalent vacancy would be created with the opposite charge. So, in this case, if a -2 charge is created, then the option would be correct is Ca2 plus. So, here it is marked wrongly, it should be option D. Question number 14, the conductivity in silver halides AgCl and AgBr when plotted as a function of divalent impurity concentration shows a maxima in the intrinsic region. True or false? This is false because it shows a minima in the extrinsic region, and this minima comes due to the fact that here the vacancy at one go you have the vacancy ion dominating another region. So, this region you have the vacancies dominating the conductivity, whereas in this region it is the interstitials, and when they become equal, then that is where you attain the minima. So, as I said, that contribution to the vacancies is equal to the contribution due to the Ag plus interstitials. So, vacancies are more in number, but they are less mobile. These Ag plus interstitials are less in number, but they are more mobile. So, there is a minima. So, this statement is false. Now, which of the following quantities are dimensionless? So, this is Heaven's ratio. We know that Heaven's ratio is the tracer diffusivity by the charge diffusivity, that is dimensionless. Isotope effect parameter, again it is a dimensionless quantity. The degree of association of vacancy impurity complex, which is P, is equal to the concentration of the impurity vacancy complex divided by the concentration of the impurities. This is again dimensionless. The jump rate of vacancy impurity complex, which is given by omega. So, omega is not a dimensionless quantity, it has dimensions of the frequency. So, here the correct option is A, B and C. Which of the following statements are correct regarding the diffusion of heterovalent impurities in alkali halides? So, the first is diffusion in extrinsic region is dominated by motion of cation or anion vacancies depending on the nature of impurity, or the B option is diffusion in intrinsic region is dominated by motion of self interstitials depending on the nature of impurity. So, in this case the option, the first statement is correct. The C is diffusivity is independent of concentration of impurities. This is wrong. Diffusivity is strongly dependent on concentration of impurities. This is correct. So remember, we are talking about the heterovalent impurities. It is strongly dependent on the concentration of impurities. Impurity vacancy complexes make contribution to diffusion at elevated temperatures. This is false because they make a contribution at the lower temperatures. At lower temperatures, you are more likely to get impurity vacancy complexes. Question number 17. Two students of this course are measuring impurity diffusion when calcium 2 plus ion is added to NaCl at room temperature. One student has added Ca2 plus such that the ratio of concentration of impurity vacancy complex to that of total Ca2 plus concentration is 1/4. So essentially the value of P is given. So the ratio that is the concentration of the impurity vacancy complex to the total concentration is 1/4. Second student has added Ca2 plus such that this ratio is 1/3. So I estimate the ratio of impurity diffusion coefficients measured by these two students. So we have seen this formula so first of all, when you add heterovalent impurities, there is a dependence on the concentration, and we have seen this formula d2 is equal to 8/3 a square omega 2 f2 into p by 1 by plus p, where p is this degree of the association, which is the ratio of the concentration of impurity vacancy complex to the total impurity concentration. So if we assume that rest all parameters are similar, then because both the students carried out at the same temperature, so then we know that P1 for the student 1 is 1/4, P2 for the student 2 it is 1/3. So if you take the ratio of D1 by D2, then it comes to be 4/5. So coming to the last question, which of the following statements are correct regarding the Arrhenius plot of tracer diffusivities of cations and anions in alkali halides? The slope of the graph is equal for the intrinsic and extrinsic region. This is not correct. You can see this is how the plot looks like. The slope of the graph is higher for intrinsic region than for extrinsic region. This is correct. You can see that the intrinsic region it is higher. Extrinsic diffusivities decrease with the increasing concentration of impurities. The diffusivities actually go up. Option C is correct because it is extrinsic diffusivities increase with increasing concentration of impurities. This is a correct statement. Whereas D, which is extrinsic diffusivities decrease with increasing concentration of impurities, it is not a correct statement. So the correct options in this case are B and C. So with this, we will end tutorial lecture for this week, and in the last lecture, we will go through the various concepts that we have covered in this course. Thank you.